We're going to practice using your TI-89 to find extrema and zeros of various functions. We're going to start with a really simple cubic polynomial that we really could do just as easily using the power rule. So if you would pause and get that function entered into y1. And now if you're back, let's zoom standard, our -10 to +10 axis. And you might choose to reset the window, but I think we can find the 3 zeros using this window. So we choose F5 and choice 2 to find a 0. And we've done this plenty of times in class already. Let's get the cursor below the x-intercept, and then we'll move the cursor for an upper bound to the right of the intercept. And it might stay busy for a second. And we've got our first intercept. Then we would repeat that same process for the second and the third x-intercept. And I've already written my answers, and notice I would keep more than 3 decimal places in the middle of the problem, since I might do another calculation with these values. All right, question B says, is there a quicker way to find those zeros in the home screen? Well, let's go to the home screen, and this is a good chance to remind you if you don't want to see what you've done previously. F1 Tools has a choice 8 to clear the home screen. And notice it did not clear the entry screen, so that's what the clear button would do. So not necessary to clear the home screen, but easier in a video if you're not seeing the work that I've done earlier. All right, so our question is, can we solve to find the zeros of our original function? So what we haven't done much with is our computer algebra system. So under F2 algebra, we have a solver. And then we put what we want to solve. We want to solve the equation y1 of x equals 0. And the easiest thing to forget is, like your derivative syntax, you need to say solve with respect to what variable. So solve this for x. So solve this equation for x. And when we hit enter, it might be busy for a little bit. But then you can see we have a right arrow here, so if we scroll up, we can find our 3 answers all at the same time. So the solver might be a nice solution for you at times when you don't want to repeat the same process 3 times in the graph screen. All right, letter C says go back to the F5 menu for this function, and let's use the options to find local max and local min. So, oops, and I hit F5 here, and I wanted to go back to the graph. Sorry, let's go back to the graph, and now from the graph screen, now I'm ready to hit F5, and let's find a local minimum. And finding a local minimum is really the same as finding a 0. We have to get our cursor to a lower bound on the left side, hit enter, and then move our cursor to an upper bound and hit enter. And it's in the interval that we chose, it's going to give us the place that has the lowest y coordinate. And the nice thing about this local minimum feature is it gives us in one operation, it gives us both the x and the y coordinate. However, we can't justify our answer saying I let my calculator find the minimum for me. So notice what I wrote here as my answer. We can see that there's a local minimum of -3 at x at about 2.000 since f prime changes from negative to positive. Well, I haven't even found f prime yet, so it's a little bit unfair for me to be using that logic. But do I already know that that's what's going to happen? Isn't the first derivative going to be negative when f is decreasing, and the first derivative will be positive when f is increasing? So you can't just use the local minimum feature of your calculator as your logic, but you can certainly use it as a quick way of doing your calculation. And then we could repeat the same thing on our calculator using the F5 menu to find a local maximum. So we could simply get our cursor to the lower bound enter, cursor upper bound, and it's going to work for any interval. It's going to find the biggest y coordinate. So it might find the y coordinate at a closed endpoint of your interval. So here you can see it's taking a little bit longer for it to find the maximum value, and you might not recognize this. Read carefully. This is exponential notation. So 1.13 times 10 to the negative 38. Well, that's essentially 0. Remember that our calculator isn't going to give us exact answers. It's going to round them off. So our local maximum is 1 for the y-coordinate, and it occurred at x approximately 0. So again, you can see that to justify my answer, I've written that the first derivative changes signs from positive to negative. So you might actually write your justifications a little bit differently than what you did with your calculator. All right, so now we've got to remember two different ways to find f prime. So we already know what f prime is going to look like. Well, we talked about the fact that you could go right to your y editor, and here we could do our shift 8 to get our derivative key, and then we could find the derivative of y1 of x, comma x, with respect to x, that is. And it will graph the derivative, but we can't. The disadvantage of this method is it'll graph the derivative, but we never see its formula. So there's our derivative function. So I told you I wasn't fond of that method, but it really depends on what you need to know. So let me go back to y2 and clear it. If you need to see the derivative function, then my suggestion was to go to the home screen and do the same thing, the derivative of y1 of x with respect to x. And once we see the derivative, we can arrow up to highlight it, green diamond copy, and then go to y2 and green diamond paste. So it's exactly the same thing, except now we can actually see the algebraic version of that first derivative. And remember, this might be where you might want to change styles. So f6, you might decide to get on this function and do f6. That would be a shift f1. And you might decide to make your derivative thicker or your first one thicker so that you can tell the difference between the two. So if I graph, of course it's the same derivative either way. But let's notice, in fact, what we said before is going to happen. So when the original f had its maximum, isn't it true that the first derivative changed from positive to negative? And where the second derivative had its minimum, isn't it true that that's where the first derivative changes from negative to positive? So we knew exactly what was going to happen. All right, so remember to justify Extrema that you must use a first or second derivative argument. All right, so how about inflection points? Well, let's go back to our graph, and let's just go to the y editor. Let me try that again. Go to the y editor, and I'm going to use F4 to uncheck the derivative so that it's not in our way right now. So the only thing we're going to look at is the first derivative, or the first function itself, and I believe it looks like it's concave down and then concave up. So I believe there's got to be an inflection point somewhere in this decreasing interval. Well, again, our F5 math menu has inflection point as one of the choices, and it's another one of those things that you can't justify on your test paper. You can't say, I let the calculator do the work for me, but it doesn't mean that you can't use this. So we can do a lower bound and then move to an upper bound, and it's going to look for an inflection point, and right here at 1, -1. At 1, -1, we find an inflection point, but notice how I would justify it. I actually have never graphed the second derivative yet, but I would be smart enough to know that it has an inflection point. F has an inflection point where F double prime changes signs. And if you're a doubting Thomas, let's go to our y editor, and in y2, let's do that second derivative. So we'll do the derivative of y2 of x with respect to x. So here's our second derivative. And if we go to the graph, notice I'm only graphing f and f double prime. And of course, right there where f had its inflection point, that is where the second derivative crosses over the x-axis. So you can verify that both ways. But remember, on your paper, you're going to justify inflection points and concavity using the second derivative. All right, are we sure there's no other inflection points? Well, that would be another good idea or a good place to use the home screen. Let's use our solver, F2 solve, and let's find out if y3 of x is equal to 0 at more than one place. So remember, we have to put this comma x. Solve this equation for this variable. And when we hit enter, it gives us only 1 point. So in fact, that inflection point was the only one that we solved. All right. Remember that solving for the second derivative equal to 0 is horrible mathematics. Just because it hits 0 is not enough to guarantee that it's an inflection point. Remember, you have to double check that it doesn't bounce there. It has to cross over the axis. But we've already seen the graph. We already know that the second derivative is negative, and then it hits 0, and then it becomes positive. So it can't be a bounce point on the second derivative. So if the second derivative changes signs, don't just say the second derivative equals 0. That's not good enough. All right. So I think we've done all of this. Let's see what comes up next. All right, now we're going to switch to another function. That's the one where I had one of my exponents in the wrong order. So I'm going to pause the video and clear my previous functions and put this new function into y1. All right, once you have that function, then look at our next direction. It says let's set our x window, green diamond window. So our x min is going to be -5 and our x max is going to be +5. Oops, and I missed that one. Let me change that scale. I hit return twice. We'll put that scale back to 1. The scale doesn't matter. Let's go -5 to +5. And then we don't care about the y-axis. Let's do the zoom feature now. It says then go to zoom fit. So you may never have even noticed this was here. Under F2 zoom, I think it's letter A. We have to scroll down to find zoom fit. And what we're saying is let the calculator, oops, and I have an undefined variable. So I'm going to go see what that is about. I'm going to pause and come back. I think I have my function typed in incorrectly. So I went to my Y editor, and you can see that it was just my typing mistake here that I have x times x. So that's not a good variable. So we have a choice here, F3, to edit a function without retyping the entire thing. So I'm just going to go here, and I'm going to backspace to get rid of that. All right, so I think I've fixed my function. Now let me go back to window, -5 to 5, and then I was going to do zoom, F2 zoom, and then choose choice 9, choice A for zoom fit. And we're letting the calculator choose our y coordinates. And then we'll see what our graph looks like here in a minute. It's busy. And to save time during the video, I've already sketched what I came up with. So you might say, how did the calculator decide this? And I'm not sure. I know the -5, +5. That should say +5 right there. And then let's go look at our window. The problem here, of course, is it looks like it has zeros all the way along here. But you'll see why. This actually could be going up and down. But our window size, let's look at it. Green diamond window. Oops, sorry. Let me Escape out of there, and let's try green diamond window again. So if you look at our Y maximum is, and this time I have 42,250. I had done this with my other calculator and had a Y max of 48,225. So, but it's got a huge range, in fact. So you can see why, if this is 48,000, you can see that even a value of 10 or 20 is going to look the same as a Y coordinate of 0. So we've got too big a window here on the Y's, and that's why we cannot tell where we're crossing the axis. So our next step says, well, let's change the window and see if we can do better. So I picked -3 to 2 for the X min, X max. And for the Y min, I picked -50. And for the Y max, I picked 100. And then let's see if we get a different version of the graph. Does that help us see whether we have minimums and maximums? And it looks like it's above the axis, but it's hard to tell when it's exactly 0. So the size of the pixels, while we think of a pixel, one of the points on the screen, is pretty small, but it represents a lot of different real numbers. So that screen is not very helpful either. So now I hope you can see why we want to use the first derivative to see what's happening, because there might actually be some minimums here under the axis. We're not sure about that. All right, so let's go to the home screen, and let's find the first derivative. So the derivative of y1 of x with respect to x. And then let's arrow up and green diamond copy that and go to our Y editor. Sorry, I'm not hitting this very well. Let me copy that again. And then let's go to our Y editor and green diamond paste. And now the window size still might not work very well. So now if I want to uncheck, let me go to the first function and only see the derivative here. You can, of course, keep them both graphed, but I'm graphing only the derivative. And if I remember correctly, it's still not very helpful because we still might cross over. We don't really know if this stays below the axis and above. It could actually have a slight positive loop and a slight negative loop. So some more zooming in is still going to be important. So our next directions say zoom in near the origin. So let's think what we want to do here. So I don't really need to change the x min and x max, but I definitely don't want to go from -50 to 100 on the y-axis. So I could zoom in here. For example, I might go from -1 to +1 because I'm really interested in where does the first derivative cross the axis. So I might not see the loops completely, but let's see if we get a better picture this time. And so we can see even -1, +1 isn't real clear, but it certainly looks like this might be a bounce point at the origin, that our first derivative hits 0 but doesn't cross over. So think what this means. This means the first function has negative slopes and then a horizontal tangent and then negative slopes again. And then it finally has some positive slopes. So when the first derivative bounces at 0, that should give us a saddle point on the original graph. So we think if we're zoomed in enough here, and we could zoom in some more, but we think that f prime has only a bounce point at 0 and then whatever this value is. So we could do that in the graph screen, find these two zeros, or since it's our new topic of the day, let's find out using our solver. So let's again solve. And our our first derivative is in y2. So be careful that you're putting in the right thing. I want to find out where y2 is equal to 0, comma, solve for x. And it'll be busy a little bit. And we come up with just two answers, and that's kind of what we expected. So notice there's no right-hand arrow, is how I know that these two are the only two zeros. All right, so we have a bounce point at 0, and then this second 0 is at our point approximately 0.32904. So I've already written these down only to save us some time as we're going through the video. So you can either find the zeros from the graph, or you can use the solver from the home screen. All right, now what else do we need to do with first derivatives? We need to test the intervals. So, and of course this graph was pretty clear. We had two critical numbers, so it gives us three different intervals from negative infinity to the smallest critical number, and then between the two critical numbers, and then on the right-hand side of the larger critical number. So if you need to test these intervals, and you might say, well, I think I could already see that from the graph. But let's say for playing devil's advocate here that you're using a function that you hadn't graphed. Could you test the intervals several different ways? So the first option, of course, is to look at your calculator, look at the graph. The second way that you could test this would be in your home screen, and you could say, well, I want to do the second derivative, so you could say, tell me the value. And now I have y1 of x here, but in this case we're actually testing the derivative, which is in y2. So that's an example. So I want to know what oops, that's not correct. Let's get that out of there. I want to know what y2 of, and now I want to choose a number smaller than 0. So how about negative 10? That's our first derivative, and our first derivative is negative. So we know that if it's negative for one value in this interval, it's negative for every value. And now let's cross over the critical number, and we could continue just doing this in the home screen, or just for sake of showing lots of calculator options, another thing that I sometimes do if I'm going to test a lot of values is I leave a generic variable x there, and then I use the such that bar, x is equal to, and then the value that I want to test will be right at the end of the statement. So for example, if I test 0.1, I can see that my y-coordinate is still negative. So two intervals in a row stayed negative. Well, we know why that was. Remember, that was our bounce point at 0, 0. So the first derivative was negative, then it hit 0, and then it was negative again. All right, and then I could simply use my right-hand arrow to get to the end of the statement and back up. And now I just want to choose a number that's bigger than 0.39. So for example, I could just type a 1 there. And as expected, our first derivative is then positive. All right, the other way, if you had a lot of intervals to test, and I think you've got a homework problem where you might have 5 or 6 intervals. So you might choose then to go to the table. So if we do, green diamond table, and I can't get there. Let's see once more if I can find table. There we go. Now 5, and now just like clearing the home screen, under F1 Tools, F1 choice number 8 will clear all the old values from the table. So are you sure you want to clear it? Hit enter. You don't have to, you can just type over the old values. Now notice that it's only showing me y2 because y1 was unchecked. So remember that y2 is my first derivative. So I wanted to test a number like negative 1. And then you have to remember here our negative 0.1, I guess I got. And then you want to go down. So you have to use the down arrow. And that's going to be our test for the second interval. And then we tested a number bigger than 0.329, like positive 1. And there's our negative interval, positive interval. So the advantage of the table method is it stays visible, and I can test all of my intervals at once, and then I can transfer my answer onto my paper. All right, let's see if we can get things finished up here. We've got just a little bit more to talk about here, and that's the concept of a numeric derivative. When you use the power rule, you find the algebraic derivative. You find the formula for the derivative everywhere. A numeric derivative is when we just want to find the derivative at one specific number. So we have a lot of choices. We were just doing that in our home screen. This, for example, was the derivative at x equals 1. So this is really how you can find f prime of 1. So there's one method in the home screen to find f prime of 1. You can just put the x value into the function in the home screen. Remember that from our graph screen, we're looking at f prime. This is our f prime graph. So if we use derivatives here, we would be finding the second derivative. So I better be careful here to make it clear that now we would want to go back and check the original function and uncheck the derivative. So now if we go back to the graph, now we're going to be seeing the original function. Remember, that's the one that was kind of flat in the middle. And now if I wanted to know what the derivative was at any value, so now if I go back to my F5 menu, I have a choice to find derivatives. So I go down to choice 6, and notice there's a side menu here. We want to find, and the others are grayed out because we're only using two variables, so it's going to be dy dx. If we're doing parametric equations, that's when you'd have more variables to choose from. And now I can move my cursor wherever I'm interested. So if I left the cursor there and hit enter, it's going to tell me the slope. The derivative at that point is -2. Does that look like a reasonable slope of a tangent line? But here's what I think is even handier for me. If I want to find a derivative at a specific point, I don't want to use the cursor because that's not going to be very precise. So if I wanted to find the derivative at -0.1, I'm just going to type -0.1, and it's going to go right into the x coordinate. And there's my y coordinate. So it's exactly the same values that you would get using the home screen. Let me do that one more time. If I want to find the derivative, so I go to choice 6, and dy dx is the only choice right now. If I wanted to find the derivative at 0.5, I can just type in that x coordinate instead of using the cursor. And there's the slope of this function. So if you use the derivative of the derivative, remember you would be finding the values of the second derivative. So you'll want to be careful about that. All right, next you've got some homework problems to practice. Be sure that you try the homework problems on your own first, and then I'll make a video of my solutions for the homework problems.